associative is an interesting thing. Yeah. So have you understood the method of how we proved that matrix multiplication is associative? Is it okay or? Yes or?
1 second.
Okay.
So we essentially showed that the elements will be the same, right, after the multiplication process on both sides.
Yes.
By
But
by defining how the multiplication happens, even though like we're taking two different. In the first case, we take B and C first, and in the second case, take A and B. Even though that order is different, at the end we arrive at the same elements.
Yes, that's right. Yeah. So that obviously, so that comes from, so what I want to say is that, so why is it true? Right? Why is it true? Right? Obviously, we have proved it. But I want to say, okay, let me first write it. Then this, it came down to this thing, which is not just coming out of the blue, right? We said how it comes. Yeah. So so yeah, this is going from L. Kidding. Yeah. So this L to N goes from 1 to N, and here K goes from 1 to N, and here L goes from 1 to N, and here K goes from 1 to N, right? So what I'm trying to say is that this LHS comes because we are trying to show these two things are equal. So we try to compare their ijth elements, and when we write out the ijth element of this, we get the LHS and nothing else, right? So we arrive at the LHS in the natural way by just writing out what it means to multiply matrices. And similarly, when you write out the RHS, you get this. Okay. And then we have to show that these two things are equal. Now you can probably show that in many ways, right? But what I'm saying is that in the end, we are able to show it by sort of say by exchanging these two summations. Do you see that? Right? We are saying that by exchanging these two summations. Okay. So how did I do it, right? I did not even write the second one. I just knew that this nice thing of associativity should come from this nice thing of commuting of two summations. Okay. Right? And then obviously you can show that you can exchange these two summations. Now I give you a heuristic reason why you can do that. Okay. But maybe we can explain that even more conceptually, why you can exchange two summations. So for that, let us try to think. Yeah, for that, let us just clarify the picture a little bit. So here we have a summation going from 1 L going from 1 to N, and this is something which, you know, we can just write as K comma L. Is it okay to write it like that? I'm just calling this whole data, this thing, just as Sk comma L, because I mean J is not really, does not come in the picture, does it? It doesn't come in the picture, right? Does I come in the picture? No, it doesn't come in the picture. So for explaining this, what we need, we go to that. That's how people are able to come up with so elegant arguments. They do these things in their heads, right? Maybe without knowing them. But point is that this AIK, the I is not needed, right? It's just a confusion there. So we write AIK as, some, let's say, TK. Now if you try to say, you know that yeah, but there is a problem. Yeah, when I try to explain like this, let us see. Okay, yeah, let us see. So what is happening here? So we are taking the k from 1 to n. So we are saying that for every k, so you fix a k, right? K, this is k equal to 1, k equal to 2, k equal to n. So I'm just trying to see if I can find a simple reason for to say in one sentence why it happens, right? So this is where the k varies, and let's say the L varies in this way. 1, 2 is a column. So what are we doing? We are saying that for every for every k you have tk, and then basically you are having this, okay? And that way you are getting this summation. But then, and the L is also going from 1 to n, right? Now what you could do, you could say that I will fix the L, right? I will fix the, but there is a certain problem. Just a second. Okay, no problem. Yeah. So it's like, you see, we are filling this array, right? So for every k comma L, right, entry, we are putting a number. So for example, when k is equal to 1, then we have this tk, right? But we have tk times L is also equal to 1, then we'll have sk comma L, skl. So it will be t1 because it's 1. So it's like t1 s1l. And similarly, you fill that array, right? So obviously you understand that you can fix the L and vary the k, and its summation will not change whether you add row wise or column wise. It's a finite summation, right? So that's what, right? So if you do this thing column wise, then what will it have, what will it be? Then we will say, okay, mm, we will fix the L for, so first L goes from 1 to n. So we will fix a column, okay? And when you fix a column, uh, and then you add along the rows. So then you let the rows go from 1 to n, and when you go to the kth row, you have to take tk times your kth row and lth column, then you have to take this. So is this okay? these two things are equal, right? So this is something that comes very naturally, and obviously you understand that you can put this tk inside also. There is absolutely nothing, right? It is just this regular exchange which is in every book, right? On summation, any chapter on algebra, this summation exchange is there. I've just tried to explain it through a picture, that's all. Okay, let us see if this we can use to get to our result. I'm trying to say that it happens for simple reason. It happens for the same reason only. And once you make the correct relabeling, the reasons don't change and doesn't become a new formula or a new, okay, again a new reason. It's not like that. So, so what does it mean? It means that, well, it means that even this k, even this aik could have been written here, right? Yes, that's what you're doing, right? That ik, that I is fixed, so that k, and for that k you are doing, and so use the same thing, right? So that gives us that this we can do. Aik. What was changing here? Obviously the L was changing. Okay, and now you see, now you can just exchange, right? It is now it's probably more obvious in a way, but let us see if we can get it from this discussion. Otherwise discussion is not useful maybe. So this is fine. So this is equal to this. This is equal to this because this is from very simple reasons. Now is this equal to this? It absolutely is. Is it not? It is, right? Because what is it? Well, that's what we said, right? So this is what was AK, what was TK? It was AIK. What was SKL? It was BKL times CLJ.
Yes.
That's it, right? So it, and my point was that it comes from the same old reasons. It's not like suddenly it's a college level proof or it's not nothing. It's not like that, right? It comes to the same thing that you can do this, which is just adding row wise or column wise, you get the same answer. In finite case, in infinite case, you don't. That's an interesting discussion on its own, but that's a separate topic which probably will not touch this. Okay, here you notice one thing, that we have not used that 2 into 3 is equal to 3 into 2. Did we use such things anywhere? No. See, we never swapped, so we never wrote this equal to BKL times AIK. We did not do that.
Yes.
We did not use the commuting of the numbers. We only use the associativity of the numbers to unambiguously write this thing. Like because see, if you write this summation, in this summation it is actually this, and in this summation that exchange we have explained, that is fine. But in this summation it will be this. But these two things are same, means because this exchange you can do that we have explained, that is combinatorial, right? But this is equal to this is associativity of the numbers. So you see that there are two things. One is associativity of the numbers and one is this very simple combinatorics. And these two things of combinatorics, maybe we can just say that that is fine. So algebraic people will say that the combinatorics is just a thing which is true. We will not argue about that. We don't even want to call it combinatorics, it's just true. Then they'll say that the associativity of the underlying field or of the underlying the place from where the numbers are coming, the associativity of that place leads or induces associativity on the object, that is the matrices. So you see that that is what is happening. If we sort of don't call combinatorics, put that into a mathematical thing, right? Right. So because see that is true, right? But the associativity of numbers, which is sort of a the assumption or whatever, that directly is the cause for associativity that happens for matrices. Okay. So
Yes. Yeah.
it is not the numbers which you can multiply and swap. That is not used. So it's a very nice thing, right? That just associativity of the underlying things leads to associativity of the higher structure. Matrices are like higher structures, right? So that is the thing. However, you see, we have to do a lot of work. But this is not how we prove these things in college maths. But we will not discuss this proof, but I will just tell you just a picture before ending. Just like in the beginning, I was telling you how uh, these things, this matrix multiplication is interpreted as row operations and so on. But also, I can give you a picture, which again can help you to know what is true. You look at this collection of matrices, okay? You want to prove things about it. You want to prove that this associativity, right? Now you see a beautiful thing now. So earlier we had one matrix and we were looking at it, multiplying it. Then now we're looking at family of matrices. But now we will look at family of matrices and we look at something else, okay? Which is family of, we will not look at this, but I'm just saying that this is what mathematicians do. We look at family of all functions from n-dimensional space to n-dimension, which is what is just functions that take n tuple and give you out an n tuple. You can imagine plenty of such functions, can't you? Right? Take an n tuple and give out an n tuple, some function that does that, some rule is fine, right? You look at this collection, okay, of all functions. Then what do? We do something very nice. We say, okay, you take a matrix and I will somehow associate to it a function in this family. Okay, and the rule will be nice that it will associate to every matrix a function. Okay, every matrix here, it will connect it with a function here on this, in this world. So you want to prove something in the first world by using something which is true in the second world. And you probably know what I'm talking about, the associativity of functions, which we know, and it's very easy to prove. I mean, function composition, right? So what we do is for every matrix, we interpret it as a function somehow. And it is a function, right? When you take a matrix, take a column vector, you get back a column vector. And so it is a function which takes n column width to and takes it to an n column as output. But yeah, this is what we do. And then we say that this association is such that if A goes to F and B goes to G, then product of A and B goes to composition of F and G. Okay, it is such a nice thing because see, the product of A and B will lie somewhere else, right? It will be some other function. It will be some other matrix, and that will go to some other function. But we are saying that this rule is so nice that it goes to composition of the functions. Okay, so product here is mirrored by composition downstairs. Okay, now there's not much to do because if you now look at this, okay, this, where does this go? This goes to F compose G compose H, right? And where does this go? Well, this goes to this. But we know that these two things are equal. And this association is sort of a bijection. It doesn't take two matrices and give the same thing. There's also reverse association. Okay, so it's a completely, proper association. And so these two things are equal means that these two things are equal. You see, you prove things about one area of mathematics using some, not so much of a thing. It's actually a very simple thing. But you can already see that what is happening. We are going to larger and larger perspectives. Okay, this is the way, but obviously
Yes.
it needs a lot of work. Like, what is that association? In the end, nothing is saved. Okay, in the end, it's the same. You will have to, do the investment somewhere. But we do the investment so that it kind of, helps in whatever. Whether it helps or we create more mathematics so that it seems helpful, I don't know. But yeah, it is. This is the thing. And then, in fact, over time, this actually also becomes a small thing, small island. And then we sort of take all other kinds of curvy functions, and we study this collection of curvy functions or continuous functions using these things. So there is another thing. So and then it goes into something else. So it's a, yeah, it keeps zooming out, and yeah. So this is the conceptual thing about. So you can basically, this will help you to know several things about multiplication, what can be true, and then when we do inverses, it's sort of composition of a function with its inverse, and so you know that what happens there, you know what to expect, what will be true at least, and then you can prove it. Even if you don't know the exact association, then you can prove it by just staying in this world. But you can compare, and you will know what can be true, what will be true. Okay, and then you can check your guess, and over time you will develop the thing. In fact, one doesn't need to know this association directly to you know to work, to know what is true here, right? You can get used to that association by studying what it gives you, right? Which is what we mostly do, right? Yeah. So yeah, that is it. And so I plan to continue this on Saturday 9 p.m. only. Okay. Yeah, but before stopping, since we have discussed some things already, you can just try. Obviously, you should try problems from all kinds of things. So I saw that you can see CMI papers or whatever matrix questions are there. But it will be good if you can just practice. If you go to the end of this chapter, you can get a taste of what kind of questions are here. Basic operations, nothing, just basic stuff. But it's a, so you can try to do how many you can do, to try, maybe. Yeah, see how many you can do. These are, because these are good problems, and apart from that, obviously there are all kinds of things you can try. Okay, but keep this as maybe your first try this Artin. So it's Artin algebra. You can download it if you don't have it. Okay, if you use PDFs, I don't need to buy this now. There's a cheap internet edition available, but since we are only going to do the first chapter strictly, there's no point. So you can just download it, and you may get a more recent edition. I don't matter. Okay, Artin was a top
Yeah.
class mathematician. His father was probably the, yeah, he revolutionized algebra. Okay, we have read his work also, Emil Artin, or probably with his mother. Anyways, yeah, Emil, I don't know, something but related, I think. And obviously this guy also. Yeah. Okay, this is a standard text. So when we start courses in CMI, this is sort of, first chapter is sort of assumed in some way. But obviously we won't do all the nitty-gritty things in the first chapter. We won't do the star problems of the first chapter, but we will try to cover it, okay, as much as. Okay,
Oh,
so that is. But we'll see you on Friday for the usual discussions, problem discussion. Okay. Yeah, Friday 9 p.m. and Saturday will be doing this.
okay. Yeah.
Okay, so Friday. Okay.